of RA in two ways, either by slope or by angle. Now, if you observe, RA is along this direction, which is parallel to this surface, isn't it? That surface is making an angle 30 degrees with x-axis or with horizontal. So we can just write that this is 30 degrees. Or what we can do, the other way, what we can do is we can find out the slope of this line, which is y is 0.26 meter, x is 0.15 meter, right? In this triangle, how do we get the slope of a line? The y and the x. So if that is the slope of the line AB, what is the slope of a line perpendicular to AB, which is RA? The slope of this line would be the flipped version of the slope given here. That means y here would become x, that means here 0.26, and x here would become y for the line that is perpendicular to AB, which is 0.15. That means the slope of RA could be written as x to be 0.15, y to be 0.26. That is one way to write, or we can give angle. Anything is fine. Now let's proceed with solving this problem. Here, now that we have finished drawing the free body diagram, that means we gave the axis, x and y, we gave the angles of the reaction forces that are not parallel to either x or y, and we gave all the distances, so we're good with the free body diagram. Now the unknown things that we need to find are RA, RB, RC, three unknowns. So in a 2D problem, this is a two-dimensional problem because we only have x and y. The equilibrium equations are sigma fx is equal to 0. Sum of all the forces in x should be equal to 0 in a free body diagram, assuming to the right is positive, implies. Now tell me, what are all the forces in the x? Let's start with the 300 newtons, which is on the far left. So that would be negative 300 sine 30 degrees. And the only other thing we have is RA, which is plus RA cos 30. That should be equal to 0 because those are the only two forces in the x direction. Now let's write sum of all the forces in y equal to 0, assuming to the top is positive, implies. So negative 300 cos 30 plus RC minus RB minus RA sine 30 degrees is equal to 0. And the third, the last equilibrium equation is sum of moments with respect to a certain point in the system. Which point would you suggest taking? We have A, B, C, and the point at which 300 Newton force is acting. We can take sum of all the moments with respect to A. There is no reason. We can take with respect to B, C, or this particular point any point would give same result. So let's take sum of moments with respect to A is equal to 0, assuming counterclock is positive implies. So when we do this, let's start with 300 newtons with respect to A. So point A is here. So this is A. Now, with respect to A, let's start with this 300 Newton. So 300 Newton, let's take the X and Y components. I'm going to start with the X component. So the X component is 300 sine 30, and the X component is like this, right? The Y component of 300 is like this, right? So this is 300 sine 30, and this is 300 cos 30. Now, what we can do is we can take 300 sine 30. What is the moment of 300 sine 30 with respect to A? If you remember the concept of moment, it is force times the perpendicular distance between the point and the line of action of force. So what is the distance between this point and the line of action of force? 0.26. Hence it is 300 sine 30 times 0.26. And what is the direction? If you complete the circle, here, that direction, and if you point out the same direction here, the direction will be counterclock. So we'll write positive. Then let's do the Y component of the force. That would be 300 cos 60 times, or should I write times the perpendicular distance. What is the perpendicular distance for this line of action of force and this point? Is nothing but the total distance, which would be 0.5 plus 0.5 plus 0.15, and the direction with respect to A, this line of action of force is like that, right? So the direction E is counterclock, so this is also positive. Next comes RC. RC times, what is the distance between line of action of RC and A? Isn't it this, which is 0.5 plus 0.15, and this is going clock. Let me take a different color. This is going clock. How did I say that? Because we draw a circle based of this to be the center, and when I finish the circle with the distance to be radius, and I just have this arrow pointing along RC, we see that it is clock. So this is negative. And then we are left with RB. RB times, what is the distance between line of action of RB and A, which is 0.15, when it is going counterclock, that is equal to 0. Now we have three equations and we have three unknowns. What are the three unknowns? Three unknowns are RA, RC, RB. Those are the three unknowns, and we have three equations. So can we solve the problem? Yes, we can solve the problem. And the way we can solve the problem is by setting up this free body diagram, and when we use the three equations to solve the problem, we can find for the reaction forces, which are RA, RB, RC. So it's your task to find the values of these three forces for this assumption. This is the task for you. Take your calculators, use the three equations, solve for the three unknowns, and find out the answer. Because maybe you require this for the quiz. This concept is required for the quiz. Now, let's go to the next problem. Draw the free body diagram of the bent rod which has a smooth surface support at point B here, and also which has a slider, you know, support or a collar support at A. There is a collar at A and there is a slider or a smooth surface support at B. For this situation, draw the free body diagram. So we have the case here. So in this free body diagram, at B, let's start with B. At B, you have a smooth surface. So what is the reaction of the smooth surface on the bent rod? It prevents the rod to enter the smooth surface. That means it gives you a reaction R at B. And what is the angle or slope? Before that, we have to assume axis. If we take the regular x and y, then what is the slope of RB? If an inclined plane has a slope 12 on x and 5 on y, then normal to the inclined plane will have a flipped version, which is 12 on y and 5 on x. Hypotenuse remains the same, 13. That's the slope. So we give the slope, we give the reaction. We are left with A. What about A? A is a collar support. The meaning of a collar is it has a guided motion. So it allows motion only along the path shown. That means along this path. It is free to slide along this or move along this path, but it is not free to move perpendicular to this. So the reaction at A would be like that. That is reaction at A. Second, the collar support would prevent it from rotating with respect to this direction, with respect to this axis. So it is free to rotate with respect to that axis, but it is not free to sorry, excuse me. It is if you look at this collar support, it can rotate freely in this direction, but it can't rotate, because we're talking about the 2D problem. In a 2D problem, everything rotates with respect to z-axis, right? Z-axis, which is perpendicular to the plane. So it cannot rotate perpendicular to the plane. That means it has a moment reaction here. It has a moment reaction there because it does not allow, due to the collar support's purpose is it will not allow the bent rod to rotate, and it will not allow the bent rod to move along the RA direction. but it freely allows the rod to translate along a direction perpendicular to RA here. And obviously we have to give direction for RA. We will use the same concept, which is, you see, this is, this is 3, 4, 5 for this direction here. That means perpendicular to it. Vertical would be 3, horizontal would be 4, hypotenuse would be 5. That's the free body diagram. That's what you'll see here. You see, if you observe, RA would be 3 in the Y, 4 in the X. RB would be 5 in the X, where perpendicular to that is 5 in the Y, and 12 in the Y, where for the inclined plane is 12 in the X. Now here on the free body diagram, I didn't show you the moment, but you'll also have this momentary action because it does not allow you to rotate here. So that would be the free body diagram. Now answer these two questions before we go to the next problem. Internal forces are not shown on a free body diagram because internal forces are equal to 0 or equal and opposite. They do not affect the calculations, negligibly small, not important. This is the right option, B. You don't show an internal force. When do we have an internal force? If you remember the concept, we have internal forces when we make a cut. If we don't make a cut, we don't represent the internal forces. The reason being, they're equal and opposite at every section, at every point where we make a cut. So they don't affect the calculations. So how many support reactions are there in this problem here? So here you have AX, you have AY, and there's a fixed support. You have a moment at A. You have, this is a roller support. That means you have a reaction like this. That means you have 3 forces and 1 couple moment. So option 4 is the right choice. So this is the chapter 11. We will continue to the chapter 12. So let's start with the chapter 12. We'll start with equations of equilibrium. So equation of equilibrium, what are the equations of equilibrium? They are the ones that I showed you here. These are equations of equilibrium. In a 2D, equations of equilibrium means that if a system is in equilibrium, these equations define, or these equations are true if the system is in equilibrium. That means sum of all the forces have to be 0 in all the directions. Otherwise, the body will be subjected to certain acceleration. So sum of all the forces equal to 0 means the body has 0 acceleration, or the body is moving at a constant velocity. Okay. Similarly, sum of moments with respect to a point equal to 0 means that the rotations are also 0. So the body is not translating from what we have here, and the body is not rotating for what we have here. So both translation and rotation on 0 is what we prove, or is what we're supposed to have to prove that the body is in equilibrium. So we'll see 2 and 3 force members. That means there are 2 external forces acting or 3 external forces acting, or 3 support reactions or 2 support reactions. So when we have these 2 different cases, how do we solve problems? That's what we'll be seeing in this chapter. For example, if you see this problem, if you see this quiz, if we say sigma fx, sigma phi, sigma m equal to 0, to be equations of equilibrium in 2 dimensions, this is what we most commonly use, because you see the moment we can take with respect to O, that means with respect to any point. This is what we generally use. So C is correct. A rigid body is subjected to forces as shown. So if you remember the beginning part of the course, when we have 3 forces acting at a point, we can reduce them to a single resultant force. We can reduce these 3 to a single resultant force. That means the system is as if there are 2 forces acting, because if there are 3 or 4 or 100 forces acting at a point, we can reduce them to one resultant force, FR1. And here we have a resultant force, FR2. So that's why we have 2 forces in the system. For example, there is a ramp which is pinned at A. We already saw this problem. How can we determine the forces acting at pin A? First of all, we have to replace the pin with its reaction forces, support reactions, that's what we call. And we have to replace the ropes with tensions. This is one tension, this is the other tension. If they're both symmetric, if they're both parallel to one another, we can treat there are 2 ropes, so we write this as 2T if we are doing a 2D problem. And we have the weight of the ramp, W, acting vertically down. So, for instance, in this case, so there is a spreader bar of a hoist, and the engine is supported by 3 chains, right? So if we take the free body diagram of the spreader bar, so we have, this is a tension, this is a tension, that is a tension. And this is the force acting on the spreader bar to balance the weight of the engine. So we can calculate the 3 tensions in the chain. So tension A, tension B, tension C. And we have to draw the free body diagram and then apply the equilibrium equations. So the equations of equilibrium are sigma fx equal to 0, sigma phi equal to 0, and sigma moment with respect to a point in the system equal to 0. This is what we'll apply once we complete drawing free body diagrams. One other thing that we need to understand is it doesn't depend on the shape of the member. For example, let's take a member which is like this, a complicated shape, but it is attached here and here. Let's say there is a system here, and let's say there is a system here. No matter what the shape of the member is, the force of this member A acting on this member B would be just a line passing from A to B. or force acting on B, force acting on A due to B is the same but opposite, like that. So we don't care about the shape of the member. For example, if you see this link here, it is like this. It is going all the way from here like that. But if we have to remove the member in the system and we have to replace this with a force, we just draw this as, we just draw this as a force acting from A to B, like that. For example, here it is anyways already straight, so no problem here, A to B. So this fact simplifies the equilibrium analysis of some rigid bodies since the direction of the resultant forces at A and B are thus known along the line joining points A and B. So irrespective of what the shape is, we just need to see the connecting ends, A and B. So this member could have been something like that, the zigzag, but connected to B. It still would be a force that would be passing from A to B. So what are the steps? Number one, draw XY axis. Number two, draw the free body diagram. Number three, apply the equilibrium equations. Just three steps. Draw the XY axis. See, for all the problems here, what did we do? We drew the XY axis and then we drew the free body diagram and then we applied the equations of equilibrium, right? So that's what we've done. So let's apply that for an example problem that is shown here. So number one, what should we do? We have to draw the XY axis. So there is a 4 kilonewton load acting at B. So the question is, find the support reactions at A and C. Find the support reactions at A, find the support reaction C. So what do we do here? First of all, we have to draw the free body diagram. Now the trick here is free body diagram of which force carrying member? Should we draw the free body diagram of AB or should we draw the free body diagram of CD? Because we are asking you to calculate reactions at A and C, and these both points are on AB, it's prudent to draw the free body diagram of AB. So let's draw free body diagram of AB. That means we draw AB, right? So at A, what is A? Is that a pin or a fixed? It's a pin. Pin means you only have two reactions. We say AX, we say AY, right? When you have a pin, we have AX or AY. Then what about C? I just told you that no matter what the shape of DC is, the DC member could have been a rod which is of this shape. Even then, no matter the shape, the force would pass from D to C. So here we have to say force is passing from D to C. Then we have 4 kilonewton here. Then we have to give the coordinate axis. It's an important step. This is X, that is Y. And are we good to go? No, we're not done because we have to give the distances. Also, we have to give the angle for FDC or the slope. Do you know the slope of FDC? Yes, we do, because this is y and that is x. So y, I'm going to adjust it as a spot. So y is 1.5, x is 1.5. If you remember, if these both are the same, we could just simplify this and write it as 1 and 1. And this should be square root of 2. 1, 1, square root 2. And this is 1.5 meter, 1.5 meter. Now our free body diagram is complete. So the next step is to apply equations of equilibrium, which are, so let's give the names. I forgot to give the names. So this is A point, this is point C, this is point B. So the equations of equilibrium are sigma fx is equal to 0, sigma fy is equal to 0, sigma moments with respect to A is equal to 0. X assuming to the right is positive, Y assuming to the top is positive, moments counterclock is positive. So these are our assumptions, because AB is at rest. So these should be true. So give me sum of all the forces in X, nothing but AX plus FDC times 1 over square root 2. So the component of FDC along x-axis, both are positive, equal to 0. Sigma Fy is AY, positive AY, positive FDC times 1 over square root 2 minus 4 is equal to 0. Sum of moments with respect, by the way, this is 4 kilonewton. We have to remember that. The last moment with respect to A equal to 0 is, you have the x component, you have the y component. X component has 0 moment because it is passing through A. So this is nothing but FDC times 1 over square root 2 times 1.5. So counterclock, so positive. Then negative 4 times 3. This is negative 4 because it is going clock with respect to A. And the FDC in the Y is positive because it's going counterclock with respect to A, where this is going clock with respect to A. And that's it, right? That's exactly what I've shown you here. If you see, so this is the free body diagram. But in the free body diagram here, the AX is going to the right, AY is going to the top. So when we solve for this, we get AX to be negative 8, AY to be negative 4. That means our assumption is opposite. We should have assumed opposite, but this is how we made an assumption. Anyways, when you get a negative answer, just leave it as a negative answer. Leave it as negative answer. And that's it. This is how we solve the problems. Now, in this problem here, how many support reactions do you have? You have 3. So in a 2D problem, can we solve for 3 unknowns? Yeah, you may say yes because we have three equations, equation 1, 2, 3. But we have to be careful. Can we apply these three equations to the problem shown here? Tell me, what is sigma fx equal to 0? When you apply sigma fx equal to 0, the x component of only this force, that would come to 0. That means you get f should be equal to 0. That means all these f's will be 0 and all these reaction forces will be 0. So if I give you any value for f, this can't withstand because there is no reaction force in the x for this, because these are all roller supports and you only have the y reaction forces and no x reaction forces. So when you have no x reaction forces, if you have an external x